second lab for Physics 2. We will begin talking about the magnetic field of a bar magnet right now. So the purpose of this lab was to investigate the distance dependence of a magnet field of a small bar magnet, and to use different formulas from this class and actually apply them to something significant, such as simulating the magnetic field of a bar magnet using GlowScript. And the data that I personally found and computed myself was the magnetic dipole moment is roughly 1.765 AM squared. The measured off-axis magnetic field is 7.8 times 10 to the negative 5t, and the simulated off-axis magnetic field is 3.01 e to the negative 5. I understand that I put off-axis twice in my presentation, but for the first off, I'm not doing it. As you can see, there are many key concepts we can discuss during this lab, such as the Boyat-Savart law and the different types of B loop and dipole and perpendicular and the derivative of B as dB. Here you can clearly see my drawing for the model of a magnetic field where the arrows are pointing away and to the magnet depending on which side it is on. I have written in black the magnetometer, and for the system, I have the magnetometer, and for the surroundings, I put it as the bar magnet. For the procedure, you need a bar magnet, magnetometer, meter stick, and tape, and then to actually measure the magnetic field, for the on-axis, we must measure distance between magnet and magnetometer, given that the magnetometer is on the on-axis to the dipole of the magnet, and for the off-axis, we measure the on-axis distance between the magnet and magnetometer, where the net magnetic field is 100t, and then proceed to record and compute the Y component of the Earth's magnetic F field, and apply this distance in the Y direction, etc., etc. So for the results, you can see that I computed them in Excel, and note the off-axis field at the bottom of my lab, and all of this data is important, and the significance says, sorry, I'm lagging. You can see the line of regression creates this formula that I put here. These are the formulas used during this important part of the presentation. And we used the formula on the left that we previously computed in the last slide to find K in the next slide. Now for the explanation. We show in this lab that when the magnetometer is far away from the magnet, you get a near zero magnetic field. So there is an inverse proportion between the magnetometer distance and the magnet. If the magnet is closer to the magnet, there is an increased magnetic field. I also made a computational model in GlowScript where you can see the observation locations code, the magnet at the origins code creation, and also the magnetic field function. You can see the end result of my experiment in GlowScript on the right, where we have the blue line pointing left from the magnet, and then an orange line, two orange lines pointing to the right. There is more code also shown on the left, which is important. As we discuss, we will find that the distance between the magnetometer and the magnet decreases, the magnet field increases. So I had at 20t, the distance was 2.22 times 10 to the negative 1. At 70t, the distance was 1.23 times 10 to the negative 1. And the magnetic dipole moment was 1.825 AM squared. And I found that there was a 74% difference between the net magnet field and the experimental data and the simulated data, which did come from my own computations and a calculator, so we know that this worked. Potential sources of error are as follows. There maybe not were enough sources of magnetic fields, so this could have distorted my measurements. People were talking too, which could have affected my presentation because of the sound waves they had put in my environment. Also, the surface wasn't fully flat, and the measurement error from the magnetometer could have played a part too. Overall, I may have had a few inconsistencies considering there was such a vast error, and light posts could have played a role. What if we haven't oriented with respect to Earth's magnetic field? First question. Both X and Y components would be different from now. For the second what if question, we see that the magnitude of the magnitude field would increase due to the combined magnetic field from the two magnets. The magnitude of the new magnetic field would be double the magnetic field of one magnet due to superposition principles, and the measured distance for each magnetic field would decrease due to the magnetic field of the two magnets. Thank you.